So this is a quick walkthrough of GLM5's architecture. So GLM5 and GLM 5.1 are the same model. It's just that 5.1 has been post-trained on more data, so it has better performance, focusing on, I think, agentic coding. So this plot or image is obtained from Sebastian Rashka's LLM gallery, which is a super nice place for you to get a high-level overview of the different major open source LLMs and their architecture at a very high level. Okay, so initially I'm just going to walk through very quickly the different components of the GLM model, and then we'll do a deep dive into sparse attention, MLA, and also how their MOE layers work. So the high-level picture is pretty straightforward architecture. You have your input that goes through a tokenizer. The tokenizer then passes things through a embedding layer. So each token has its own corresponding embedding. And post this, you have a bunch of decoder blocks. So I think, GLM has 78. You can see the number 78 here, decoder blocks. And each of these decoder blocks have the same internal mechanics, right? So internally, what happens is you pass it through an RMS norm layer, and then you pass it through a multi-head latent attention layer, and then through a sparse attention layer. So it's a bit confusing here because it says attention for both. So the actual attention computation happens inside this DeepSeek sparse attention layer. And it's sparse attention because rather than using attention over all the tokens in your context window, the sparse attention layer, what it does is it picks the top 2048 tokens and using a simple weighting mechanism that I'll show later, and masks out all the other tokens from the attention op. And even before you do attention, they make use of MLA, which is a mechanism to reduce your KV cache size by basically having this latent vector that's stored inside your KV cache, which can then be projected by a linear layer to restore the KV specific heads. So that way, in your cache, you only store this latent tensor, which is much smaller than all of your heads, and all of your heads multiplied by the head dimension. And that makes things much faster. And then they also have a MOE layer instead of a standard dense MLP. And in the MOE layer, what you have is one shared expert. And then besides the shared expert, all of the tokens are routed to 8 experts. So in total, they have 256. So you can see here 1 to 256. So in total, they have 256 different MOE experts, but we only choose the top 8 experts for any given token. And besides that, if you dive deeper into each of the individual MLPs inside the MOE, it's a standard swig glue. So you have 3 linear layers going through intertwined with a SILU activation layer. And one thing that's not highlighted in this specific image is the fact that rope is kind of broken down into partial rope. So what that means is, so the internal hidden dimension size of your QKV tensors is 256, but the first 192 dimensions, they don't go through any rope operation, and only the last 64 dimensions go through rope. There's been a bunch of papers on investigating the right way of doing rope. So it's just another small mechanism where, so having no rope kind of helps with very long context, and having rope helps with the shorter context when you actually need to know need to have the positional information of the tokens. Okay, so that's a very high level overview. And now we're going to dive deeper into the 3 main modules that are different from your generic LLMs, so that we understand what it takes to implement them, and also identify areas for creating custom kernels where we can do stuff like fusion, for example, or even stuff like having parallel CUDA streams to overlap computation of different things. So these are the defaults at a glance. I think this is good to keep in mind for all of our kernels. So all of our kernels should be specialized for these specific shapes, right? Because we're not supporting all models. We just want to focus on one specific model. This means that all of our kernels can specialize to these specific hyperparameters. So the first one is vocab size, so 154K. This is different from Quen 3, which was around, I think, 250K. So like the vocabulary size is much shorter. And then your hidden size is 6,144, 78 layers. So this is the model's depth. Total number of attention hits is 64. Yeah, so you have a bunch of different LoRa layers. You have a LoRa layer for your query vectors. You have a LoRa for your key and value tensors. And you also have a LoRa layer for your indexer that probably, yeah, I'll walk through a bit further down the line. And yeah, this is your head dimension size for when you basically perform attention. And this is like the key thing to note that I mentioned about rope. So your query and key tensors are so it's always the Q and K tensors that go through rope, right, for positional embeddings. But like I said, the first 92 dimensions don't have any rope applied to them. And then the last 64 have rope applied to them. But if you add these two up, it's equal to 256, which matches your head dimension, which is where like how attention is going to be computed. And then the total number of routed experts is 256. Like I mentioned, experts that you route to is 8, one shared expert. And within your like MOE MLPs, the intermediate size, so your up projection linear dimension size is going to be 2048. Oh, and the other thing that I forgot to mention is, so GLM has this interesting property where the first three layers have like this completely dense feed-forward networks. They don't have MOE, and it's only the last 75 layers that have MOE in them. So that's why you have this difference between the intermediate sizes. So this is the intermediate size for all of the MOE layers, and this is the intermediate size for all of your first three MLP layers. This is just MLP layer types, whether it's dense or MOE. So first three are dense, the other is ML3. This is not being used. It's not being used, so you don't have to worry about it. This is like a hyperparameter that's used in the indexer that I'll come to later. And this is like the number of tokens we choose for sparse attention. So it's like 2048, like I mentioned earlier. And these are like some properties of the indexer. Again, I'll come to that later because the indexer is quite like jam-packed with a lot of stuff happening inside it. Okay, so the very first thing that happens once we are out of the token embedding layer is even before RMS norm is you have to basically get your query key value tensors, right? So in a normal like in a standard transformer architecture, what this would mean is just going through a simple like linear layer where the hidden state goes through 3 different linear layers for getting like query key and values as tensors. But in GLM5, it's quite complicated because all of them have their individual LoRa layers. So the query tensors, the key value tensors, all of them have their individual LoRa layers. So first, let's just focus on the query side. So the input is the hidden state, and it has like 3 different like layers which are being optimized or have parameters to them. So this is basically your like down projection layer. So it takes a hidden size and then down projects it to the LoRa size for the query. So this goes from 6,044 to 2,048. So you're compressing it, right? So it's becoming smaller. So it's being compressed to a latent. And this latent is going to be used later by the indexer. So it's just important. Yeah, it's good to keep that in mind. And then after this process, you have your like layer norm, and then your up projection layer to restore the query to basically the number of heads you want during attention. So that's what you see here. So your small compressed tensor is going to be up projected to number of heads we have, so 64, into the QK head dimension, which is 256, kind of what I mentioned earlier. So we have 64 attention heads, each with your head dimension. And like implementation-wise, this looks fairly straightforward, right? Forward pass, hidden states go through a forward pass to get the compressed like query representation. Then you pass it through a layer norm, and then you pass it through the up projection layer. And then what you have is you have batch size into sorry. Okay, so now you have like this 256 dimension query tensor, and then you can split it into the fraction which needs a rope and which doesn't need rope, right? So that's what you do here. You take your query states and you're saying split it on like the nope dimension and also the rope dimension. So this is 192, the first 192 dimensions, and this is the final 64 dimensions. And then you finally apply your rotary positions, your rotary embedding to this the portion, the 64 dimensions that you only want to apply it on. And at the end, you have like batch size into head, into number of heads, which is this like -1 here. And then followed by sequence length, which is like the same dimension as like the hidden states, right? S over here. And then D, which corresponds to your head dimension. So QK nope head dim plus rope head dim, so which is 256. And yeah, so then again, this is like the shape walkthrough. Yes, so 6044, after your down projection it becomes 2048. After layer norm stays to 4048, and then after the up projection, you have 16,384, which you can reshape to match your number of heads, which is what happens here, the V plus transpose, and then you split it to identify like the nope and the rope dimensions. Okay, so now your query tensors are kind of prepared and they're kind of ready for attention, but you have to do the same. You have to do something similar to get your key and value tensors as well. And again, very similar to what happens in rope. In query, you have this lower layers. So the very first one is like this down projection thing, and there are a few important caveats to keep note of. So first is you're creating like a single like key tensor that can be used for rope. So it's not going to be in two head dimensions. So this is like similar to multi-query attention, where you have multiple like query heads, but just a single key head, right? Or key and value head. So this is like the initial down projection, and this down projection is going to be what creates the latent tensor that's going to be stored in your KV cache. And after that, standard layer norm, and and the next step is, okay, now I have my latent tensor. How do I get the up projected tensors that I can use for attention? So what you see here is it takes the latent tensor's input size as input, but the output is going to be the total number of attention heads, so number of heads, into my like query key head size, nope size, because you already have the rope here, and then the nope size plus the V head dim, which is 256. So that's a bit confusing, but if we walk through like the code, it becomes like much simpler to kind of like wrap your head around. Okay, so first down project to get these latent tensors, right? So you have this notion of K compressed and K positional embeddings. So what you need for your rope. So K compressed is what goes through your KV cache. So it is just a single head of size 512. So it's important to note that it's just like a single head. So it's not like into 64 heads. So again, that's where a lot of this compression is coming in, and where you're getting a lot of savings on your KV cache, because you just stored a single head of size 512 for each of your token positions. And then, okay, so the next step is, okay, now I have this compressed key tensor. How do I get it to a stage where I can apply attention, which needs like number of attention heads into like the dimensional head size that matches the query tensor? So this is where this up projection layer comes in. So you pass it through the up projection layer, and then you reshape it to match batch size, sequence length. -1 is total number of heads, and then this is your like final dimensional size that you need for actually performing attention, right? And similar to what we did above, we're going to like separate our value states from the key states. So this is the sum of those two things. So you have your key and value tensors basically like merged into like the same tensor, but now we just want to separate them because they're going to be used differently in attention. So you split them up based on their size, and then you identify like your k-nope and your value states. So yeah, this matches, right? So value is the same shape as your attention, as your query now. So this is perfect, but your K is still not complete yet, because so this only is k-nope, which has 192 dimensions, but you need to make it match 256. And the way you do that is by taking your KPE from earlier and then like basically merging those two. But before you do that, you have to apply rotary embeddings to your KPE. And again, like just to reiterate, KPE is just one head. It's not multiple heads. So the same head is going to be broadcasted across all of the heads. And this is what you see here in your expand. This is where broadcasting happens, where you broadcast across all the heads needed for attention. And finally, you're doing the concatenation of nope and the positional embeddings to get your final query key states. And your value states are already in the right shape. So they don't have this notion of nope or rope because value tensors don't go through any sort of like positional embedding stuff. Okay, so now you have your Q, K, and V tensors that you need to perform attention. So the next step is for attention. Oh, okay. And this is like a quick math on like the savings that you have by using this MLA technique, right? So if you weren't using MLA, you would have to store like 32,768 values for key for K and V. So this would be like the number of like floating point data points, right? And with MLA, you just have to store 576 because all you do is store K compressed and KP and nothing else. So that's where like you get this huge savings on memory. And also a quick caveat. So right now, Hugging Face's implementation for KV cache doesn't support like latent MLA, basically. So it stores the entirely materialized tensors, but that's like a 2D on their side. It shouldn't affect us because VLM has its own like optimized implementation where they do actually use MLA and store the right KV cache. But that's just something for us to take note of. There's a significant difference in implementations between VLM and Hugging Face. So while Hugging Faces is good for like high level understanding of architecture, the actual thing that we're competing against is VLM's own custom implementation of the same architecture. And that's what we need to familiarize ourselves with later on. Okay, so now you have your QKV tensors. The next thing is before we do attention, because GLM5 uses sparse attention, we need to understand how like this sparsity comes from, right? So like I said, there's this module called the indexer. And what the indexer does is it identifies the top 2048 tokens that it needs to perform attention against. So these 2048 are basically your entire previous context window, right? So all the tokens that have been seen in the past that are relevant for the current query token. And the way it does this is with this overly complicated like formula that basically is a variant of attention, but it gets rid of it gets rid of a lot of the like the heavyweight operations in attention, like softmax, for example, so that you can avoid like a lot of the complicated operations. And I'll do a deeper dive now into that. But before we get started, again, it has this LoRa type of structure. So there's going to be like a down projection matrix and an up projection matrix. And similar to attention itself, it has its own configuration for the number of heads that it uses. So each query token produces 32 heads, and these 32 heads basically determine how much like effort or attention that you should pay to each given key token in your context window. And it has similar like rope semantics sort of thing to what we just saw about, but it just operates on like a slightly smaller dimensional size. So earlier we saw that your query key tensors were a size 256, but here everything inside the indexing module is going to be a size 128, so half the size. And all of your like LoRa matrices are initialized to accommodate this size. Okay, so at a very high level, like all these are all of the different like modules with parameters that are being initialized. So one, you have this query side projection. So what it takes is it takes your like the low rank query tensor that we saw over here. Yeah, so this is the input. So this Q res ID is the input to the indexer. And this would eventually go down to, yeah, this Okay, it comes later. Sorry. Yeah, sorry. So this layer, what it does is it takes the Q resid uh, tensor that I mentioned about, and then it produces like n heads into a head dimension, right? So it produces like uh, 32 heads of like this 128 dimensional size that'll be used for getting attention scores for how much importance each query gives to each for how much importance a query gives to each given key tensor in your context window. And then you have another like matrix that is supposed to produce weights to assign to each of your heads. So this is like a learned head importance factor. So it takes the hidden size. So it takes your like hidden layer as input, and then it produces 128 different scores corresponding to each of your head dimensions. And then again, you do like a layer norm in between. And yeah, this weight prediction layer gives the importance at the number head layers layer level. So you have 32 heads, and we want to get like an importance factor for each head that's being produced by this specific like layer. And this is the standard like normalization factor that's involved in the attention op. Nothing, yeah, nothing different here compared to like standard attention. Um, okay, yeah, and this is what happens in the forward pass. So first, let's see what how we get the right queries, right? Pass it through this layer, which gives us like 32 heads of shape 128 dimension each. And then again, similarly, split to like nope and positional embeddings, and then apply the positional embeddings to this specific tensor, and then concatenate to have like this nope and rope fused together. And now what happens next is, okay, how do you prepare the query tensor? So the query tensor goes through WK. So the input is your hidden state, and it produces a single key. So just a single key, not 32 heads. So it is like a single head of size 128, similar to all of your other 32 heads in the query side. And then you basically, yeah, do the same. Hey, like, let me apply rope. Let me concatenate this after post rope. And then the final thing that happens is you do attention against Q and K, but because it's on this like much smaller dimensional size, it's kind of faster in many ways. So this is what happens here. Like you're performing einsum over the sequence, over the head dimension to basically get like the importance scores of the query against each of your heads. And then instead of using softmax, they use ReLU because softmax is like a very complicated operation that involves that it's not like a pointwise operation, right? Because it depends on all the other like scores as well. Whereas ReLU is like a pointwise op, so it's like much faster, much simpler. And after you obtain the scores, you basically multiply these scores with the weights that that your weight prediction layer gives you for each of the heads. So this again very similar to like how attention is computed over the value tensors. Once you get the attention scores, the same principle. And once you have like the index scores, you do a top K to get like the top 2048, and you identify those indices, and then you did I not include? Oh yeah. So yeah. And after that, so after you identify like the top K indices, you basically scatter those indices importance scores through your attention mask. Identify, okay, like anything that's not a like a negative infinity has to be basically included in attention, but anything that does have like an infinity doesn't have to be included in attention. And that's where the sparsity comes from. And flash attention makes use of this to actually perform sparse attention. Whereas if you use something like I think STPA out of the box, it doesn't actually use sparse; it does full. But like I said, in GLM, they have this. They have the integration with the right backend of flash attention to make sure that it makes use of the sparseness. So you make sure you compute attention much faster when you use this technique. Did I miss anything else? Oh yeah. The other important thing to note is that so the MLA has its own cache, but even this indexer is going to be caching stuff itself because the key tensor here needs to be cached for every new position ID, because you're going to be reusing it for your attention over here, right? Because you need the entire sequence length of keys. So you also need to cache this key tensor every time, which means that you need to have like a separate cache for managing the indexers cache compared to just the MLA's cache. So that's the other important thing to keep note of. All right. Okay. So now we have attention done as well. The final thing to do is to pass it through an MLP. So like I said, the first three layers are like your standard dense MLPs. There's nothing fancy about them, so I'm not gonna like dive into it. And the last 75 layers go through your standard like expert-based mixture of MLPs. So you have one shared expert, which means that all tokens are always going to be routed to this one shared expert, right? And an expert is nothing but like an MLP with just a smaller intermediate size. So if you take a look at how things are initialized, so an MLP basically has like these two layers, up projection and down projection. And you have, number of experts, so 64. So each expert gets its own MLP layer, basically, right? And followed by 2 into intermediate size, which is like the project size. The reason why you have this 2 into is because Silu has 2 linear layers at this site, so 1 and 2, which is so you just pack them into like a single linear layer just to make things more efficient from like a GPU hardware allocation point of view. And then you have the down projection layer, which restores the shape to the hidden dimension size. So again, nothing complicated over there. But in terms of routing, the only, I guess, minor like interesting thing in the architecture is that, so once you have your like your router logits, and the way you get the router logits is by you have a linear layer. I can just show the code here. Yeah, so you have a router which is nothing but basically like a single linear layer. And what it does is it takes your hidden states and it produces scores for each of your experts. So it produces like 64 different scores. If you take a look at it here. So it takes hidden size as input and it produces 64 different scores, which is basically like a important score assigned to each expert, right? And then what you would do is you would do a top K operation over those scores. But before you do that, the way GLM does this is similar to a DeepSeek. It adds this expert correction bias. So this is actually a parameter that's learned during training to do load balancing, which is basically a way of saying that, hey, I want to make sure that all of my experts roughly have the same number of tokens passed to them, rather than like all the tokens being passed to the same expert. So you don't want to bottleneck things. This also helps from like an inference point of view, because when you do like multi-GPU inference, what you have is expert parallelism, which means that different groups of experts reside on different GPUs. So if you have all of your tokens being routed to the same expert, it means that the same GPU is going to be used and all the other GPUs are going to be idle. And that's not great, right? So with this correction bias, you basically ensure that, roughly speaking, like all tokens are routed to like the same number of experts. And sorry, you're ensuring that each expert roughly gets the same number of tokens routed to it, so that the load is balanced. So after accommodating for this correction factor, you do a top K operation. And then the other interesting caveat is, okay, so you've picked the top K indices, but rather than using these scores as the weights, what you do is you actually use like the uncorrected scores for getting the top K scores. So if you do like, you see here, you're doing a score start gather on scores rather than scores and underscore pick, which means that the scores is not taking into consideration the correction bias, right? So the way to think about this is, okay, for me to choose which experts to be routed to, I'm going to make use of scores underscore pick. But once I've picked my experts, the actual weights that are going to be assigned to them is going to be based on the original scores themselves. And followed by that, they just have this like hyperparameter for like scaling this. I'm not exactly sure why they need to do this. That's something I'm missing. So, okay, here it says that without the rescale, the MOA's branch computation to the residual would be bounded by a single expert's worth of activation, which is too small. I'm not sure I understand that. Okay, something for us to figure out later. All right. Anything else? Okay, yes. And like this is Hugging Face's like naive implementation of how you would basically dispatch each of the tokens to the experts. But this is a for loop, which means that it's bad. And realistically speaking, people have like custom MOE kernels that basically use something like a grouped gem operation to avoid this for loop and to avoid like all of these launch related latency overheads. And yes, GLM has its own, again, MOE backend for like optimizing this part. So this is like just a naive implementation. Okay, the final step is, okay, so now we have identified which experts we want the tokens to be routed to, but we also, if you remember, like I mentioned that GLM also has like a single shared expert. So we also need to pass our original hidden states to the shared expert, and then you finally like add those two together. So this hidden states is after you pass it through the MOE layer. So if I go over here, yeah, so you can see that your hidden states come from your experts initially. So this is all the after the experts routing has been done, and then you pass it through like the and then you add it with the shared experts, which uses the original hidden state values. Okay, so this is like a full forward pass through one decoder block, and the same thing happens over 78 layers, right? So yeah, so that's pretty much it there. That's the architecture of GLM5. So the most like interesting like modules are the indexer and also the MLA layers. And I think this is probably where like we have like scope for like really good optimizations. But besides that, there are a bunch of like different fusion things we can apply, right? So for example, if you go back to the way the K tensors are being computed here, for example, so this entire block and this entire block are kind of independent from each other. So they can either be fused or they can be their own like CUDA streams running in parallel. So that's like one optimization like thing that we can look into. There are a bunch of other like fusion opportunities as well, like even within the indexer, right? Within the indexer, this block and this block is kind of like completely independent from each other. So again, you can have them be run in parallel. There's also something on the input side where, so the very first step where, yeah, so like all of this logic as well, until you pass it through your decoder, all of this can be fused into like a single kernel as well. But, and I do believe that GLM is like doing all of this stuff as well in terms of like the fusions. But like these are just some that like the areas that I've identified. But the first thing to do would be to like dive deeper into GLM's implementation of the same model and understand all of the fused kernels they have, and identify opportunities of like improving those places. But yeah, this is all I wanted to walk through. I hope that this gives everyone like a good like high level overview.
In the first three layers, you said they were different in that they don't use MOE, right? Is that the only difference? Yes. They use the same type of attention as the rest of them.
Yeah.
I wonder why they do it that way. I wonder why they have these special first three layers. Like what they think they're doing, why they pick three.
Yeah, it's all hand wavy conjecture. It's like this worked when we trained stuff. Like that's kind of what it boils down to, empirical evidence of how good the loss curves were when they trained stuff.
Do you have a sense of like why they split up the rope embedding in the way they do?
So yeah, there have been a bunch of papers showing that if you don't like include rope, you have like better performance on really long context windows. So that's like the major reason.
And this is like a middle ground.
Yeah, exactly. Yeah.
I also noticed was interesting that they don't compress the weights for the indexer. They use FP16, not FP8, and that's a clear sign that how important that is. That even the tiniest error will just send it in. It just show how important that indexer is going to be.
Yeah.
It's pretty cool. You don't want to show us the cool animation?
Yeah, so this is how you restore your Q and K and V tensors. Just walking through like all the operations that happens and how the shapes kind of change. And yeah, this is what the indexer kind of does. Yeah, you take your Q from your previous, from the previous slide, and then you get these 32 heads of shape 128, and you split it into rope and nope, and then you basically get your K tensor with just one shared head, like MQA style, and then you get the important scores over all the queries or over all the keys. This is how like your experts are chosen. It's just showing like 8 experts being picked out of 256, and it's added with the final shared expert. But yeah, it's pretty much. I think it gives a good overall picture after you've gone through the doc.
Awesome. It looks like something out of an Apple keynote as well.
Yeah, I just asked it to create like an animation in the style of 3 blue, 1 brown.
Nice.